Good afternoon everyone and welcome to another worked exam answer video. Today I'm having a look at a GCSE question on structure and bonding. Now it doesn't specifically tell you which structure and bonding, it's given us some melting and boiling points for some halogens and we have to explain the trend in the boiling point which is caused by their structure and bonding. And I've chosen this question because it is a nice 4 marker to start off with. Part B is a really interesting question in its own right, and the first part of explaining that trend is not the easiest thing to do. Structure and bonding questions are hard, notoriously. We can trip up on our wording, use the wrong words for the wrong type of forces that we're trying to describe, and that can prove quite costly. So I just thought that this would be quite a nice one to do. And this particular question comes from an AQA paper, but this kind of stuff will come up across all GCSE specifications, I would presume. I know it certainly does come up in the Edexcel, iGCSE and OCR as well, from my recollections, but this specifically is an AQA question. So, as I have said, we have got the melting and boiling points of some halogens in this table here. And the first question, we have to explain the trend in the boiling points of the halogens shown in table 1. Now the first thing, we haven't been told what the trend is. So it says explain the trend, but the first thing we're going to have to do is state what that trend is. So the first thing that I would always just check is that they've given you the elements in some sort of order. I would presume that they would give you the element at the top of group 7 first and then work their way down the group, which they have, but I feel like that's always just something worth checking out. So fluorine is at the top of group 7, chlorine's underneath it, bromine's underneath chlorine, and then we haven't got iodine or astatine or tennessine on there. You certainly won't get the last two. So we only have to describe and explain the trend in the boiling point for the first 3. So what we can see is that as we go down the group, the boiling points are increasing. So fluorine will be a gas from minus 188 degrees Celsius. Chlorine will be a gas from minus 35 degrees Celsius. Bromine won't become a gas until 59 degrees Celsius. So fluorine and chlorine are both gases at room temperature. Bromine will have melted by the time we get to room temperature, but it certainly won't turn into a gas, it won't boil. So that in itself is useful, but here we can think about as we go down the group, there is an increase in the boiling point. And I said this question was about structure and bonding, but it never once mentions structure and bonding here. So how do I know that? And how are you supposed to know that, I guess, is the key question. Anytime we are explaining melting points or boiling points of anything, whether it's different elements on the periodic table, whether it's compounds, particular type of compounds, anytime we are thinking about explaining melting or boiling points, it has to come back to structure and bonding. So bonding wise, we've got covalent bonding, ionic bonding, metallic bonding, and then in terms of structures, if we've got covalent bonding, there's the choice between giant covalent structures and simple molecular structures. For ionic bonding, we've got giant ionic structures, and for metallic bonding, we've got giant metallic structures. Now, we need to also therefore know when we get covalent bonds, ionic bonds, and metallic bonds. And our halogens, they are in group 7 on the periodic table, they are non-metals. So that is pretty key to know that they're non-metals. When we have non-metals joined to each other, which we do here because all of the halogens are diatomic, so that means the atoms move around in pairs. So it's not just F, it's F2, it's not just Cl, it's Cl2, it's not just Br, it's Br2. We're going to have covalent bonds in between the 2 fluorine atoms, the 2 chlorine atoms, and the 2 bromine atoms. So that's the type of bonding that we've got. That means we either have to have a giant covalent structure or a simple molecular structure. And these are not going to have giant covalent structures because each molecule is only made up of 2 atoms. And to have a giant covalent structure, we would have hundreds of thousands, if not millions, of atoms joined by covalent bonds. So that is the first thing that I would suggest anytime you're being asked about melting and boiling points, melting or boiling points, to think about what type of atoms we've got. Are they elements? Are they compounds? And then once you've identified the type of bonding from that, is obviously then to put that with the type of structure. And with covalent, it is tricky because you've got to decide between giant covalent and simple molecular. The only giant covalent ones, graphite, diamond, silica, they're giant covalent. Graphene as well for AQA, which is one sheet of graphite or one layer of graphite, but everything else simple molecular. Okay, so the first thing I'm just going to put here is covalent bonding, and then simple molecular structures. And that's going to help me with my explanation, because as soon as we know that they're simple molecular structures, it's actually not the covalent bonds between the atoms that we're breaking. With a simple molecular structure, what we're trying to do is separate the molecules. So if I had 2 fluorine atoms joined by a covalent bond, I'd be trying to separate one fluorine molecule from a second fluorine molecule, and that would be the same for all of the fluorine molecules in the sample. And then chlorine, we'd be doing the same thing. We'd be trying to separate not the chlorine atoms from each other, but one chlorine molecule from another chlorine molecule. Same thing with bromine. Now you might be noticing what I'm doing here as we work along from fluorine to bromine, and I will explain all, but this is going to help us again with our explanation of why the boiling point increases as we go down the group. Okay, so I will label those atoms once that highlighter's had a moment to dry. So the first thing we're going to need to do is describe the trend. So as we move down group 7, from fluorine to bromine, the boiling points increase. Then in terms of this simple molecular structures, if we're not breaking the covalent bonds and we want to move the molecules apart from each other, what forces are we therefore thinking about if we're not thinking about breaking the covalent bonds? Now, between molecules, we have intermolecular forces. Inter meaning between, molecular molecules. So intermolecular between molecules makes sense. If we were to say intermolecular forces between atoms, it would be very wrong, because between the atoms, that's where we have our bonds. And the covalent bonds are very different from these intermolecular forces. First of all, covalent bonds are incredibly strong, whereas these intermolecular forces that I've drawn with these dashed lines are very, very weak indeed. And that is key in terms of why all of the halogens have low melting and boiling points compared to other substances, but we're not thinking about other substances, we're thinking about the comparison of these 3 simple molecular structures. So we're going to need to mention these intermolecular forces between the molecules, and I would want to get in there as well that they've got simple molecular structures. So I'm going to say the halogens have simple molecular structures, or you could say that they are simple molecules. with intermolecular forces between the molecules, and it's these which need to be overcome in order for us to separate the molecules and boil the halogen. So I'm going to put that here. Which need to be overcome. Now, all of the halogens have the same intermolecular forces between the molecules, but what you might have noticed when I was drawing my molecules is that my fluorine atoms in the first diagram are a lot smaller than the chlorine. Slightly bigger. I could have made a bit of a better distinction between the fluorine and the chlorine, but certainly with the bromine it becomes more noticeable that the size of the bromine atoms is bigger, and therefore the overall size of the bromine molecules are bigger. Why is that important? You can see that the intermolecular forces, so the surface area across which those intermolecular forces can exist, is bigger between the bromine molecules because the bromine molecules are bigger, because the bromine atoms are bigger. Now, intermolecular forces, as I've said, they're all weak and they're certainly never strong, but we can say that we have weaker or stronger intermolecular forces. So as we go down the group, the strength of the molecular forces increases because the size of the atoms and the molecules increase. So more energy is needed to overcome the stronger intermolecular forces. Still not taking a lot of energy, but it's certainly taking more than it did for fluorine. And that is the fundamental explanation as to why the boiling points change. So it's not that some have got intermolecular forces and some haven't. We need to first of all identify they've all got intermolecular forces, but that the intermolecular forces differ in strength between the fluorine molecules, the chlorine molecules, and the bromine molecules. So let me get that worded down. The other thing that I'm thinking about putting in here is in terms of the bigger atoms or molecules. We can think about the MR of the overall molecules. We can think about the total number of electrons in the molecules, because it's the movement of the electrons that helps to generate these intermolecular forces. So that's why I've paused. So the intermolecular forces get stronger as the halogen atoms and thus molecules get larger, and there are more electrons / a higher MR. So more energy is needed to overcome the forces. That is really quite tough. Thinking about simple molecular structures and intermolecular forces is never very pleasant at all. But here we're looking at different strength of the intermolecular forces, whereas I think when we're used to doing comparison questions, when we're thinking about different boiling points and why this might have a low boiling point and this has a higher boiling point or melting points, it can often be that we're describing different types of structures. So this has got strong covalent bonds, whereas this has got weak intermolecular forces. But not here. Here they're all intermolecular forces, it's just we've got stronger intermolecular forces as we get to bromine, because the bromine molecules, because the bromine atoms are larger. Okay, hopefully that makes sense, but if not, please do not hesitate to ask, and also please do not hesitate to draw a diagram in your answer. there is nothing to say that you couldn't draw that and then annotate around that what I've written here. So yeah, diagrams are always something you can do, and if you find that helpful and a bit more visual and easier to explain, go for it. Now in part B, the interesting question on its own says, why is it not correct to say that the boiling point of a single bromine molecule is 59 degrees? That is because at the boiling point we would be separating bromine molecules from each other, and we can only boil the bromine if we fully separate numerous bromine molecules from each other. If we only have one single bromine molecule, then there's no intermolecular forces. If there's not a second molecule, there's nothing attracting the two molecules because there's only one. So because we're not breaking the covalent bonds between the atoms, when we think about boiling points of diatomic elements like the halogens, we're thinking about the amount of energy needed to separate molecules, not separate the atoms within one molecule. So the boiling point actually reflects all of the bromine molecules and separating all of them from each other to give us a gas. Okay, so it's not correct to say that the boiling point of a single bromine molecule is 59 degrees. Okay, so bromine molecules would be more accurate as we're overcoming intermolecular forces which do not exist if there's only one molecule. We're not breaking the covalent bonds, we're separating the molecules. If you only have one bromine molecule, you're not really giving an accurate depiction of what is going to happen at the boiling point. So that was quite an interesting one. This is quite tricky, so as I said, please do not hesitate to ask if anything I've said is unclear. Thank you so much for watching, guys, and I hope you all have a brilliant week.